Okay, let's talk about neighborhoods and basic topology. Topology is the study of continuous functions and limits. Calculus tells us how derivatives and integration work, but to do that we need limits. So we have to start with some basic topology in order to build up what we mean by what is a limit. And to get to what is a limit, we need to know what a neighborhood is. So let's start with a metric space. A metric space is any set that we can put a metric on, and the metric, remember, we had that it's positive in identifying, it's symmetric, and the triangle inequality holds. So we have a set X and we have a metric D. So this is our metric space. We can usually think of this as the set of reals with our absolute value as our metric. That's a really good example to always have in the back of your head. Would this work with real numbers? What does it mean with the real numbers? Or maybe even R2, the Cartesian plane. What's it mean for points to be close to each other? And the metric in R2 would be the Euclidean metric, the square of the difference in the x values squared plus the difference in the y values squared. Okay, square root of that. So we start with a metric space, and then we have a neighborhood. A neighborhood is all of the points that live close to another point. So a neighborhood of P of radius r, and we're going to denote it n sub r of P. That's going to be the set x in x such that the distance from x to P is strictly less than r. So this is stuff in x that's within distance r of P. Okay, so it's just what lives nearby to P. Let's look at the real line. Say I have the neighborhood of radius 1 about the point 2. So let's look at the real line. Here's the point 2. Anything that's within 1 of 2 means that I could go 1 that way, or I could go 1 that way. On this side I get out to 3. On this side I get to not negative 1, to positive 1. And so our neighborhood about 2 of radius 1 is this interval from 1 to 3. Not too bad. Okay. Okay. In R2, what a neighborhood. So neighborhoods in R, they look like intervals. They're open intervals, right? This inequality here, it's strict, making them an open interval. In R2, what do we get? Well, let's draw the picture first. Okay, so I have this point P, and I can go R away from it, so I get to go R in any direction. I end up with this open circle, and everything inside that open circle is in the neighborhood. This is n sub r of P there. It's the interior of a circle of radius r centered at P. So the equation we could write down would be xy such that the square root. Well, let's not do the square root. Let's just go with x minus p1 squared plus y minus p2 squared is less than r squared. So it's the equation for a circle, except for it's not an equation, it's an inequality here, and it's an inequality that gives us the interior of that circle. We'll call it the disk. They're open disks. Since the circle is the boundary, right? The disk is the interior. In R3, it's well, it would be the interior of a sphere. Sphere of radius r, centered at P. We call these balls. And in higher dimensions we still call them balls. So the neighborhood of radius r at P is a ball in Rn. We can call it a ball in R1 or R2 as well. It's just more commonly called a ball in higher dimensions when we can call them disks or intervals in 1 or 2. But we've got these neighborhoods now. So what does a neighborhood do for us? Well, it allows us to define what it means to be a limit point. So I've got these open circles. So let's look at an example first. And I'm going to take the sequence 1 over n. So 1, 1/2, 1/3, 1/4, and so on. And let's see if we can figure out what the limit of this sequence is. So I'm going to draw this on a number line here. Here's 0. Here's 1. I'm going to put a point. There's a point at 1. There's a point at 1/2, at 1/3, 4th, 5th, 6th, 7th, 8th, and so on, right? There's points all the way throughout here. The limit of this sequence well, we all know that to be 0, right? As this sequence gets bigger and bigger, or as goes farther and farther out, the numbers get smaller and smaller, they get closer and closer to 0. So how are we supposed to define that with these neighborhoods? Well, 0 is the limit, so everything should be kind of close to 0. This sequence lives close to 0 because at 0, if I draw a big ball, there's definitely red points inside that ball. But no matter how small I draw this, there's still going to be red points inside that ball. So 0 is a limit. Of 1 over n, this sequence here, n equals 1 to infinity, since every neighborhood of 0, no matter what the radius is, every neighborhood of 0 contains points from the sequence. Okay. Let's actually prove that. So let's look at a neighborhood of 0. Let epsilon be greater than 0. So here is the point. This is going to be our radius. Of the ball, the neighborhood. At 0. We need to show no matter what epsilon we have, there's a point from the sequence inside neighborhood sub epsilon of 0. Okay. Neighborhood sub epsilon of 0. This is the set of x in R such that the magnitude of x minus 0, the distance from x to 0, is less than epsilon, right? Which just says that the absolute value of x is less than 0. So it's the set of all things that have absolute value, less than epsilon. Absolute value can't be less than 0. Okay. So we just need to find something in the sequence that satisfies that relationship. By the Archimedean principle, since epsilon is bigger than 0, there exists in the natural numbers with n times epsilon bigger than 1. Right? Why did I choose 1? I chose 1 because I want epsilon bigger than 1 over n. I needed to figure out what n would work. The Archimedean principle says that there is one. This shows that 1 over n is in the neighborhood of epsilon about 0, making the intersection non-empty no matter what epsilon we chose. Okay, and that's the end of our proof. That proves that every neighborhood about 0 contains a point from that sequence, so 0 is the limit is a limit point for that sequence. In fact, it's the only limit point of this sequence. But every ball we chose around here contains points from the sequence. No matter how small it is, there's a red dot in those circles. Okay, so let me write what a limit point is definition-wise. If a set E is a subset of a metric space X, P in X is a limit point of E if every neighborhood of P contains Q in E with Q not equal to P. So there's some number or some point Q inside the set not being P. Right? So let's look at some examples. So here's a picture. Here's our set X. Here's our set E. Maybe I've got some solid boundary, some open boundary. Maybe I've got a point over here, maybe sort of another little chunk here. Okay, so which points are limit points here? Well, let's draw these in. So this point, every circle I draw around this little pink point is going to have stuff inside of E, right? There's stuff over here. Every circle, there's going to be some intersection that's not exactly that circle. So all of this stuff, everything on this boundary, these guys are all limit points. Stuff inside here is also limit points. Okay? Stuff inside here. This stuff is limit points, and the boundary is limit points. These two guys that are isolated, these are not limit points. Why aren't they limit points? It's because if I draw a little circle around them, this point, it doesn't intersect E except for at the point itself. So that guy right there, he's not a limit point. Neither is this guy, because there's a circle that doesn't intersect E except for at the same point at where the circle is centered. Okay, so limit points, they can't be isolated from E. They have to sort of be part of E. There has to be a circle, and there has to be significant stuff inside that circle that's contained in E. Alright, so that's our definition for a limit point. Let's talk about closure. So the next basic topological definition is a closure. A set E is closed if it contains all of its limit points. Okay, so let's look at some examples of closed sets. So here's X again. Just a point by itself has no limit points, so a point by itself is closed. So let me call that A. This is closed. How about something with a partially closed boundary? It says partially closed, so why is this not closed? Call this guy B. Let's do this in a different color. Okay, B is not closed because these guys here, they're limit points, but they're not inside B. So those guys aren't closed. What about something that's sort of a solid circle? Say C. This guy is closed. The exterior and the interior, those are all the limit points. They're all right there. Okay. If I just have sort of a boundary, maybe that's my set. That's not a solid thing at all. This thing's not closed. Right. Maybe. Right. There's points in there, but they're not in. I mean, there's. Say that would be a point that would be in the limits. This would be a limit point, but it's not inside the set, so it's not closed. on the reals, if I have a real line, we call a closed interval something like this. Why does this contain all of its limit points? Well, this would be a limit point because every little circle I draw around it contains stuff inside the interior. This guy, a limit point, every circle you draw around it contains stuff inside the interval. Every point inside here, no matter how small of a circle I draw around those points, it's going to contain other stuff inside the interval. So all of these are limit points and they're all inside there. This guy is open because this point right here, this is a limit point, but he's not inside the set, right? Because I can draw circles around this. No matter what circle, there's going to be stuff inside that circle that's in the interval. So this is a limit point, but he's not inside the set. Okay. Next definition is going to be the interior of a set. So a point P is in the interior of E if there exists epsilon bigger than 0 with the neighborhood of that size around P completely contained in E. So there is a neighborhood around P inside E. So let's draw our number line and see why this, or what the interior is. Say we've got this half closed interval. Anything inside here, I can draw a little circle around it that stays inside there, right? Stays inside there. Here, stays inside there. There's always like a little bit of wiggle room between you and the outside, right? The point that's not in the interior is this point right here. He's not inside, he's on the boundary. Not in the interior. Because every circle you draw around him has stuff outside. Right. To be in the interior, I just need to find one circle that's completely inside there. To show that that's not true, you have to show that every circle does not stay inside the interval. Okay, so that's interior. A set is open if every point in the set is in the interior of the set. So there's always some wiggle room. There's always a circle you can draw around a point in the set. So as long as you can always draw circles around these points, you'd be in the interior, you'd be open. This would not be open because if the boundary is contained in there, there's a circle on the boundary that contains stuff that's in the set and not in the set. No matter what circle around there I would draw, it's not there. So interior points, boundary point. Okay. Here we've got an open set. No matter what you pick, you can always draw little circles around those points. Okay. So it's open in the sense of there's space to spread out in. Every point has some radius that he can swing his arms around in and stay inside the set. The complement we talked about, I'm just going through definition 2.18 in your books. A set is perfect if E is closed and if every point in E is a limit point of E. A perfect set is a set which is closed and every point in E is a limit point of E. Seems kind of like a weird definition. I'll let you guys try and come up as an exercise. Find a set that is closed and not perfect. Okay. Two more, and then we'll be done with some of these basic definitions and move on to some other stuff in the next video. So E is bounded. So bounded means it's probably not infinite. It's bounded if there's a point, let's say Q in X, and a radius M, call it capital M, sort of for maximum, such that the neighborhood of that radius M around Q contains E. So if E doesn't get outside of a circle, it's going to be bounded, right? I've got this set X. If this is E, as long as I can draw a big enough circle, everything in E is bounded. That's fine. So let me draw something in R2 that's maybe unbounded. Let's take the set, this thing here, let's call this E, equals the set X comma X, such that X is a real number. This set is not bounded, since we can't find a big enough circle to contain it. Right? No matter what circle we draw, there's going to be stuff that's outside of that circle. Draw a bigger circle, there's still stuff outside there. So that's an unbounded set. A bounded set, you can draw a circle around. And lastly, a set is dense. Right. We used this term when we were talking about the rationals, and we said that the rational numbers are dense. And that was because between any two numbers, I could find a rational inside there. Well, intervals on the real line are neighborhoods, right? So every neighborhood contained a rational. That's what makes them dense. A set is dense if every neighborhood in X contains points of, contains at least one point of E. Okay. So as long as every neighborhood in the set contains a point, you have a dense set. Alright. So that's going to be our basic topological definitions. In the next video we'll see some examples and we'll do some things with these.